All right, Euler's number is the letter E, and you have memorized that for your formula madness, so you know at least what the value is. Mm-hmm. We're doing 8.3. Let's get started. All right, let's find the number E. I have a chart. You don't have to draw the chart if you don't want to. You can use your table of values. I'm going to actually suggest that you do. I'm going to suggest that you get into your y equals on your calculator. Put a parentheses, 1 plus 1 over n to the n. That should look like some kind of application problem that we just did. What does that kind of look like? Yes, compound interest. We're going to go parentheses. I'm going to have you get out of that now. Don't graph it. Okay. Get into your table of values, which is right above the graph. I want you to type in a 10. And what the calculator does is it puts a 10 in for x and then spits out what the y value is. Right there. Oh. Okay. What'd you guys get?
2.59.
What did we put in?
10.
5937.
You went further. Your calculator went further, right? I just rounded.
Yeah, okay.
Okay? So that, if we put 10 in, what if we keep getting bigger? What happens if we put 100 in?
2.7.
Yes. All right. What do we know that E is? You guys memorized it.
2.718.
2.718. What if you put 1,000 in?
2.716. Oh, 2.7169 or 717.
Okay. Now, 1,000 is 10 to the what power? Do you guys know?
Third.
Yeah, this is 10. This is 10 to the 1. This is 10 to the 2. This is 10 to the 3.
It's the number of zeros.
It's the number of zeros. 10 to the 4 will be 10,000. So you could just put 10 to the 4 instead of having to type all those zeros in.
Mine converted it until I got to the 10 to the 6th, and then but yeah.
So what is 2.718? Is it round? Is yours rounded?
Yeah,
2.71?
7.7181.
81. What about 2 to the 5th?
2.7183.
And then 10 to the 6th. Mine are
2.7183.
And so it's getting closer to that 2.718. And it's
those last two are both 2.7183.
okay. So the value, if you were to keep going to bunches of higher powers, you would get E, and E is approximated there.
Number, or,
well, there's not an exact in a sense. It's like pi. It keeps going. And so what you just did is if n could get to be the highest number possible, which there isn't a highest number possible, it just keeps going forever and ever and ever. But as n, or in your case on your calculator, x, gets higher and higher and higher, this equation gets closer to the value of E. Euler, a man named Euler, figured this out. And this is E, by the way. And this is not just some random thing, 1 plus 1 over n to the n. It's found in a lot of different things. It's called E, and it's named after him. Euler, it's got an E at the beginning of his name. He's a Swiss Christian mathematician. He was you should look him up. He's kind of interesting. Mathematician. His name's Leonhard Euler. He came up with this. There's lots of uses. We're going to go over one today. It's also called the natural base. It's found in nature. Populations, air pressure. This is some pictures of him if you're a little interested. There's him, and then here's him also. If Isaac was here, he'd tell him he was an aristocrat, which I'm very sure he was. Euler was a committed Christian and apparently a biblical literalist, as well as being arguably one of the greatest mathematicians ever. We're going to graph E. I'm going to tell you that it's growth. We're going to have an R value for E up there. We have an A is the y-intercept. E is like the fraction or the not fraction we've had before. If R is positive, we're going to have growth. If R is negative, we'll have decay. You might want to write that down. The A value will always be positive.
Okay.
Again, A is your y-intercept, and R is positive for growth, and R is negative for decay. All right, here is what just plain old e to the x looks like. Where does it cross the x-axis at? What do you think? What's the A value for this?
1.
1, and this is crossing at 1. And this is going to be growth. Notice that if I made y to the negative x, it's now decay. what I mainly want you to get out of this is that the y-intercept is at 1, because it's the number that's in front, the invisible number in front, and that decay is when it's negative and growth is when it's positive. Okay? All right. All right. Number 1, is number 1 growth, decay, or neither?
Oh, huh? That's
It's decay.
Decay.
Go ahead and do decay. Number 4.
Growth. Oh, no, I thought that was 2. I'm sorry.
Number 4, growth, decay, or neither?
Decay.
How do you know?
-3.
-3, it's decay.
Wait, what?
Number 1 was decay. Number 4 is decay. And Natalie, again, why is it decay?
Because of the -3.
Because of the -3. If our value is negative, then it's decay.
Okay.
All right? What about number 6, growth, decay, or neither?
Growth.
Growth, because
The R is positive.
R is positive. The 5 there is positive. Yes. Number 9. This is the first time we've had to do domain and range on any of these, and asymptotes. All right. Where is e to the x's asymptotes? Did you notice when we were seeing it on the graph earlier?
Almost 0.
What does it get close to?
0.
0. So what's the equation of that? So y equals 0, or x equals, which was it?
Y equals.
Y equals. So the equation of the asymptote is y equals 0. Okay. I'm going to suggest that these e to the x ones you actually do on your calculator and get some table of values, because they're not going to be any of them. The only one of them is going to be nice is the y-intercept. And what is the y-intercept for this one? 1. The rest of them, just get a decimal value. You can put a -1 or 1. It's up to you. You know it's going to go a growth, but when you put in a 1, you got the letter E, 2.718. So we're going to come over here to 1. And at 1, 2.718 is 2.718 is about right there, I think. And then we know the asymptote is there. We're just going to go like that.
So you only want
I only need 2 dots.
Beautiful.
Okay.
I don't like lots of little.
Now, the domain and the range. Domain. If you put a line up and down, vertical,
all points.
all real numbers. Oh, can't do that. Swirly whirly. Just do an R. Okay? All right. Then we go range.
Wait, what?
Nothing. All right. Now our range. What's our range? Oh, yeah.
0.
Wait, what?
What numbers if I put horizontals, am I touching the graph yet?
No.
No.
Greater than 0.
Great. Is it equal to 0?
No.
No, just greater than 0. Okay.
We just put like 0, 1.
Do you understand? Okay. Let's do number 11. Yx plus 1. E to the x plus 1. What's the plus 1 going to do to the graph compared to the number 10? Or 9, excuse me.
Move it to the right.
Move it to the right, I heard. You could always check on your calculator to verify. Just get in there and put a plus 1 at the end.
I moved it up 1.
Moved it up 1. Does that make sense that it would move it up 1?
Yeah.
How would we move it to the right one?
Add to the exponent rather.
Yes, so it would be e to the x plus 1 up there. That would have moved it to the left one. But,
Okay.
all right. So this is going to move it up 1. So where's my asymptote going to be then?
At 1.
What we can't just say 1. We have to have an equation. So is it x equal 1 or y equal 1? Y equal 1. All right. And so we're going to have, it's instead of being at 1, our y-intercept is going to be at 2. And instead of 2.718, it's going to be at 3.718. Does that make sense?
No.
Everything just got moved up 1. So this value right here was at 1, but we moved it up 1, so our next value is going to be at 2. You could, if you'd like, to plug a 0 into your table and verify that.
Yeah.
Okay, and then we said over here our point was 1.1 comma 2.718. It's just going to be moved up. So it's going to be 1.
So 1 is actually on 2. I see what you're saying.
So it'll be 1 comma 3.718. And I'm going to just do a little dotted line. I'm just going to put it invisible. It's really invisible, but I'm going to draw it kind of like a dotted line. That's going to be my asymptote, just so that I don't get close to that when I'm drawing it, just to help me draw it. You don't have to put your asymptote in there. I just did it for myself. So what's my domain?
All real numbers.
All real numbers. And my range?
Y is greater than 1.
Yes. Very similar to my domain and my asymptote are going to go together. Okay? All right. You've seen this formula. A equals P, 1 plus R over N to the NT. We use that for compound interest. We use that for if we were compounding annually, semi-annually, quarterly, and daily. But there is one more way to compound. Continuously. Every instant that there is. We can't calculate an N for every instant there is. But if you remember when we were putting in the values for that E looked very similar to this compound interest. We noted that. And that value was getting closer and closer and closer and closer to the E value. So our compounding continuously will be our new equation, which will be A equals PE to the RT. Some people like to call that PERT. I didn't make you memorize this one.
So what am I calling this?
You're compounding continuously. PERT. P is your principal. R is your rate. And time is for the number of years. E just stays E in your calculator. Okay. Let's do one. We're going to find the total value of our investment. We're going to be putting in $1,920 at 5.6% compounded continuously. For 2 years, round 2 decimal values. So we're going to use, I'm going to just put the A equals, P is the principal, our initial value, just like it was before. E to the RT. P is my principal, the initial value, 1920. E is just E. R is 0.056. I'm going to put a parentheses around it because we also got to multiply that by 2. Time, which is 2. I would put that in parentheses. You have to put that in parentheses because E has when you put E in your calculator, it automatically has a caret for it. Mm-hmm. So you're going to just type that in. I do not need you to do anything else after you write that. Put it in your calculator and get a value for me.
$2,147.54.
Verify that.
So the continuous, well, the E equals the continuous.
Yes.
Okay.
Yes, that's right. So anytime it says compounded continuously, you're going to use this PERT formula because it had that E in it. Yes. All right, you learned what E was. You already knew the value of it, but now you have somewhere Y. We learned how to graph. We used it to compound continuously. And hope that's been helpful. Bye-bye.